Okay, so welcome to this video. What we're doing here is we're looking at questions from the SACE Specialist Mathematics Exam from 2019. And in this video we're going to be looking at question 13 from that exam. So this is from part 2 of the exam, which are a little bit more involved. It's just got 5 questions in booklet 2, questions 11 to 15. And so this was a question that involved doing a little bit of integration and understanding a little bit about taking the inverses of functions. So it starts off with a figure, 12 here, and it shows a graph of the function g of x, which is, we're told, the function arc sine of x squared over the domain x going from -1 to +1 inclusive, and the figure is basically showing that. Okay, now part A had 2 parts, and the first one was explain why g of x does not have an inverse. Okay, so why does g of x not have an inverse? And if we look at g of x, if we go back to the previous page, we can see that what an inverse means is if you've got some function, say in this case g is a function of x, it means for any value of x in the range from -1 to +1, we can have a look and find a value of the function. So if you look at this graph, if you take any point along the axis here, you can go up and it meets just a single point. Okay, so that's a single valued function. But what we have when we take an inverse is we're going to turn that the other way around. What we're going to do is we're going to look along the y-axis, find a particular value of y, and then we want to know what value does the inverse of g take. And if we go over here, we can see there's a value. But if we go left, there's another value. So if you draw a horizontal line here through y equals 1, then there's 2 possible values. It's not single valued. So the way that we would say that is we would say that g of x is not 1 to 1. So g of x is not 1 to 1. So for example, for y equals 1, there are 2 possible values for x. Okay, and if you have that sort of situation, then the function can't be defined to have an inverse because you don't know which one of those 2 values you want the function to, or the inverse function to adopt. And part 2 of this, it says explain why f of x, which is a different function, okay, g is the first function, f is this new function, it's also equal to arc sine x squared, but it's only over the domain from 0 to 1. So we want to explain why that does have an inverse. And if we go back to the previous picture, what they're effectively saying is if you get rid of, say, this part of the graph here, if that's not there anymore, and all we have is the graph on the right-hand side, then the function now is 1 to 1, right? Because if you go up and choose a particular value of y, say there, and you draw a horizontal line, it's only going to pass through your function once because the left-hand side is not there anymore. Okay, so now the function is 1 to 1. Okay, so let me just get rid of that. F of x is 1 to 1. For example, for y equals 1, there is just one possible value for x. Okay, and in that situation you can take an inverse. Now we're given another figure here. Figure 13 shows the graph of the function f of x. So this is the graph of y equals f of x, and what we're asked to do is on the axis sketch the graph of the inverse of f of x. Okay, and what happens with the graph of an inverse, and you can see that they've conveniently drawn the line y equals f of x, and the inverse of a function will be a reflection through that line. Okay, so when we plot this graph, it's basically going to look like if you'd replace that dotted line with a mirror. And what you would see in the mirror is something that looked like that, maybe a little bit more. And so that would be y equals f inverse of x. Okay. And part 2 and 3 of B, we want to write down the exact domain of f prime of x. Okay, and so the key thing we want to know is what's the end value. So when x equals 1, then f of x is equal to the arc sine of 1 squared, which is just 1, and that's equal to pi over 2. And obviously when x equals 0, f of x equals 0, so domain goes from 0 the domain of the inverse of f of x is 0 is less than or equal to x is less than or equal to pi over 2. Okay, we want to find the equation. Sorry, I won't write the question now. We want to find the equation of the inverse, and what we need to do here is just a little bit of algebra to rearrange the equation. So we've got y equals f of x, and we write that as y equals their function, arc sine x squared. Now we want to turn this as x as a function of y, so we want to make x the subject of the equation. So the first thing we'll do is take sines of both sides, and we'll swap things around, so we get x squared is equal to sine y. And now we can take the square root. X equals the square root of sine y. We're only interested in x being positive. Okay, we got rid of the x equal negative with this function f because g had both sides. It had basically the plus and the minus, which is why it wasn't 1 to 1. But now we're only interested in the positive square root. And now that we've written x as a subject to y, what we're going to do is swap x and y around again. And that's how we write f inverse of x. So we want to write f inverse as a function of x, and so we'll swap x and y around in our previous line. And so f inverse of x is the square root of sine x. Okay, because f inverse of x is a function of x. Okay, now what we want to do in part C, it says that if y equals the arc sine of x squared, then x squared equals sine y. That's actually part of a step that we did in the previous question. Use implicit differentiation to show that dy dx is equal to 2x over the square root of 1 minus x to the 4. Okay, so we've got x squared equals sine y. And so when we differentiate that, we're going to differentiate with respect to x. And so the left-hand side becomes 2x. That's just taking derivative with respect to x. The right-hand side is a sine, so that becomes a cos of y. And because we've taken a derivative of something which has got a function of x inside, y is a function of x, and so we have to use the composite function rule. And when we do that, we need to multiply by dy dx. Okay, so that's just differentiating using the composite function rule on the right-hand side. And on the left-hand side, we've just differentiated with respect to x, just a straight polynomial term. And now we make dy dx a function, the subject of the equation. And to do that, we need to divide by the cos y term. Okay, so that's the first bit. Now the next bit is we need to make some sort of substitution for cos y. And to do that, what we're going to do is take this first line and square it. So if x squared equals sine y, x to the 4 is equal to sine squared y. And we know that sine squared is equal to 1 minus cos squared. And so when we rearrange that, let's put that again, then rearranging this, we're going to get that cos squared y is equal to 1 minus x to the 4. So y is equal to, cos y is equal to the square root of 1 minus x to the 4. Okay, and now we're going to substitute that back into what we had on the left-hand side of this page. We've still got the 2x, and now instead of cos y, we're going to have square root 1 minus x to the 4. Okay, and that's basically what we're asked to show. Okay, so we did an implicit differentiation to get dy dx equals 2x divided by cos y, and then we needed to substitute cos y into a function of x. Okay, so we did that okay. Now, part D is we want to use integration by parts, okay, to show that the integral of x arc sine of x squared dx is equal to a half x squared arc sine x squared plus a half square root of 1 minus x to the 4 plus c, where c is some constant. Okay, so to do this we're going to need to use integration by parts, and just to remind ourselves what happens with integration by parts is that we're going to integrate, so we're integrating some functions f and g, and so if we have f times g prime, that's going to equal f times g minus the integral of f prime times g dx. Okay, now in this case it means we're going to have to integrate one of these two terms, either the x or the arc sine x squared. Now we've used implicit differentiation to take the derivative of arc sine x squared. We don't yet really know how to differentiate to integrate it, so it makes sense to let f equal the arc sine x squared and let g prime equal x. Okay, and so let's write that out. X arc sine x squared dx. So we're going to let this guy here, that's going to be our g prime, and this is going to be our f. Okay, and so we're going to get f times g, so we need to integrate g, and we know that the integral of x is 1/2 x squared, so we're going to write half x squared, that's our g, and we're going to need to multiply that by our f. Our f is still arc sine x squared, and then we're going to have a minus sign, and we're going to have to integrate g, which is 1/2 x squared, times the derivative of our arc sine x squared. Now from the previous question, just go back, we just showed when y equals arc sine x squared that dy dx is equal to 2x divided by the square root of 1 minus x to the 4. So we're going to put 2x over the square root 1 minus x to the 4 up here. Okay, so that's the first part done. Now what we're going to do, well, we can't really do much to that first term. That's 1/2 x squared arc sine x squared. And this left-hand side, we can cancel the 2 and a half. They cancel each other out. And we get x cubed over the square root 1 minus x to the 4. Okay, so that's really quite handy there, because now what we have is a term that needs to be integrated, but you can see if we were to make some substitution like u equals 1 minus x to the 4, then the term above there is some sort of relationship to that. When we take a derivative of x to the 4, we're going to get 4 times x cubed. And so we have the thing on the numerator exactly what we want to make that an exact integral. So if we look at that, what we're going to have, because it's an exact integral, we're going to have a coefficient, in which case it's 1/2, because you get a 4 and you get a that you need to divide by, but you have to multiply by 2 because of the 1 minus x squared to the minus 2. The minus disappears because there's a minus coming out from the derivative of 1 minus x to the 4. You get minus x minus 4x cubed. So the minus, those two minuses cancel to give us a plus, and we get 1 minus x to the 4 plus some constant, which is what we were expecting to find. And you can see, well, we have this hint, because in this question they actually told us what the answer was. We can see from the hint up here that 1/2 is that coefficient, but you can easily check that by differentiating. So when you differentiate this term, you're going to get 1/2, so this becomes 1/4, and the 1 minus x to the 4 becomes, instead of being to the power of half, it's to the power of minus a half, so it goes to the denominator. But you have to also multiply by minus 4x to the power 3, and the 4 cancels with the quarter to give us a zero coefficient, a coefficient of 1 on that term. So you can check that when you differentiate the term here, when you differentiate this guy, you get the integrand that we were where we started from. So because differentiation and integration are like inverse functions or inverse operations, that's enough to be satisfied that we've done our integral correctly and we've come up with the right coefficient. Okay, and last part of this question is we just want to do an definite integral. So that was an indefinite integral, so there was a constant there and we didn't have any limits. Now we're going to do a definite integral where we have a limit. And most of the work's been done because we've worked out what the indefinite integral is of x times arc sine x squared dx. We want to integrate from 0 to 1. Okay, so we're just going to take our indefinite integral and evaluate it at the endpoints. So we get x squared, I've lost the arc, and plus a quarter, and the square root 1 minus x to the 4. We need to evaluate that at the endpoints. We don't need to worry about the constant because this is a definite integral. The constant at the two endpoints is going to cancel each other out. Okay, so at the upper endpoint we've got x equals 1, and at x equals 1, x squared is equal to 1, and the arc sine of 1 is pi over 2. So pi over 2 times a half is pi over 4. And the next term, when x equals 1, you're going to get 1 minus x to the 4, and 1 to the 4 is 1, so 1 minus 1 is not, so that term cancels as equals 0. Now, the lower boundary, or the lower endpoint, we've got x equals 0. In the first term, it's got an x squared out the front, so it's going to go to 0. We don't have to worry about that. The second term is just going to be the square root of 1 times a half, so that's just going to be 1. And so we're going to have to minus a half. So they're the two endpoints. The integrand evaluated at those two endpoints. Oh, sorry, not the integrand, the indefinite integral. And if we want to put those over a common denominator, we've got to multiply the second term top and bottom by 2. And so we get pi minus 2 all over 4. Okay, and that's basically it. So that's question 13 in all its parts. If you've got any questions about any of the steps that I've done here, or answering any of these questions, or you want to give any comments on other sorts of questions that you'd like to see covered, then leave a comment in the video comments below. If you want to see when new videos are coming out, which I'm trying to get out roughly once a week, although some weeks I don't always find the time to put one of these up. But if you want to get notified when they do come up, then don't forget you can subscribe to the channel and get notifications on when new videos are posted. And if you like the video, just click on the like button. All right, until next time, I'll see you later.